Okay, welcome back again. Even though we're having a great deal of difficulty uploading these videos, I figured we'd just keep going. I hope you get to see them soon. Today, this particular video is sequences, and it's an aside. None of this is calculus. You don't have to watch it. You can just turn it off right now if you want to. This is all things an aside. I just want to talk about some common sequences. Guess we'll start with Fibonacci. I think you're familiar with the Fibonacci sequence. The rule is you start with 1, the second number is a 1, and then you add every one to, you add the two previous, the next one will be 3, and then 5, 8, add these two, 13, 21, etc. I think it's 34, 55. It just keeps going, of course, indefinitely. Here's one thing about the Fibonacci sequence. You pick any flower. Go outside and pick a flower. Count the daisy. Count them. There'll be a Fibonacci number. Flowers are all Fibonacci numbers. You go out and pick something in nature, it'll be a Fibonacci number. In other words, the number of petals on a daisy. 21, 13, 34. You count them. That I'll guarantee you. There's also something else about Fibonacci. The ratio of a to n plus 1, a to n, is this number called phi. Or phi, actually. People, I think I pronounced it wrong because of the song. This number called phi, which is approximately, by the way, 1.618, I think, I forget. You could do it. And so all we're saying is you take the ratio of any one of these two, the limit, a to the n plus 1 over a to the n, as n goes to infinity, is this irrational number, phi. 1.6, I think, 1.8. Something like that. And that irrational number, it turns out, shows up everywhere in nature. Da Vinci's Vesuvian Man, there's a drawing by Da Vinci, you can't quite see, with a big circle around a naked man. That all has to do with this number right here, which, by the way, is called the golden ratio. It's quite common in Greek architecture. Hey, do yourself a favor. Just go look up the number phi. P-H-I, the number phi. And all kinds of things are going to come up. And then there's another one. Let's do, how about Pascal's triangle? This, not much longer, I don't think, of this aside, just a couple of things. Here's Pascal's triangle. There's the rule. Then each row starts with a 1 and ends with a 1. And then you get the number in between by adding these two. Starts with a 1. Add these two. Add these two. Add these two. Starts with a 1. So this would be called the 5th row. By the way, this is the 0th row, 1st row, 2nd row of Pascal's triangle. It goes on indefinitely. Pascal's triangle has a lot of, in the binomial theorem, it has a lot. But essentially what this is a table of combinatorics. If you're pressing this button, if you're taking a statistics class, and you're pressing this button into your, or a number class, and pressing that button in your calculator, that number's going to show up in Pascal's triangle. So that's that one. Then there's things called arithmetic sequences. I don't know if these are wherever, but arithmetic, where each number has a common difference. Let's call it a common add-end. Meaning you start with something and then you add something. I'll add 3. 4, 3, 7, 10, 13, 16. I'm just adding 3 each time. They're not very interesting. It has a common add-in. They actually talk about a common difference, D, and they subtract each one. And that goes up indefinitely. Then there's something called geometric sequences, which have a common ratio. 2, 4, 8, 16, of course the powers of 2, 32, 64, 128. etc. That's a sequence. It's called geometric. It has a common ratio. We will be working with these actually because we'll be working when the ratio there is 2 and it's going to diverge. But if the ratio is less than 1, we'll talk about that. Then it'll converge. Then just one more. This is called the hailstone sequence. And it's one of the most simple, unsolved mathematical. The sequence involves one of the most simple, unsolved mathematical problems that we're faced with right now. It's called the Collatz conjecture. And the Collatz conjecture, I'll get to it. I'll make that conjecture at the end of this. But so what the rule is, you just choose any number. Choose any a whole number. And then if that number is odd, you take the number and you multiply it by 3 and add 1. If that number is even, you cut it in half, thereby generating a sequence. Now, I'm not sure how well you're understanding that, but let's give an example. How about choose, for example, 12. Choose 12. Now, that's up to you. That's part of the conjecture. So we go this number that you choose. So I chose 12. Let's see, 12. And then I'm going to generate a sequence by this rule. 12 is even, so I cut it in half. 6. 6 is even, so I cut it in half. 3 is odd, so I'm going to multiply 3 times 3 and add 1. 10 is even. 5 is odd. 5 times 3 plus 1. 16 is even. And there it goes down to 1. If you take 1 and multiply it by 3 and add 1, you'll go to 4. This is called the cycle of this function sequence because the conjecture every whole number, the cycle of every whole number contains 4, 2, 1. Try it with anyone. Here, let's do 19. I'll do 19 up here. 19, I'm going to go pretty fast because I do. 19 times 3 is 57, 58 divided by 2. 29 times 3 plus 1, 88 divided by 2. 44 divided by 2. 22 divided by 2. 11 times 3 plus 1, 34. Divided by 2, 17 times 3 plus 1, 52, divided by 2, divided by 2, 13 times 3 plus 1, 40, divided by 2, 20, divided by 2, 10, divided by 2, 5 times 3 plus 1. And that's the cycle, that's the orbit of the number 19 is this whole sequence of numbers right here. The conjecture states that it doesn't matter which one this is. Every single one will cycle down to 4, 2, 1. That's unproven. We don't know if that's true. We certainly have tested it for every single number that we've tried, but we don't know that there's not one number out there that diverges that doesn't cycle to this. So that's the Collatz conjecture, tantalizingly close to being able to prove that, but it really does prove difficult. See you next time.